Welcome back. We are now essentially moving on to the next module, though I am not really following it in a very structured way, but if you look into the content, we sort of had a pretty exhaustive discussion on introduction, and certain questions like what is nano, what is so unique about nano, what is the application of nano patterned surfaces, these things we have looked into some bit of detail. Stability of thin film is something that I am keeping for the end. I mean, we need to have some more concepts before we can talk about it. Then we did talk about application of nano pattern surfaces, and in certain cases the science associated with it. Particularly, we have discussed the wetting behavior on the pattern surfaces. And you now know about structural superhydrophobicity, you now know about issues like Cassian-Wenzel state of wetting, etc. Then we moved on to discussing some of the basic concepts, and you now know surface and interfacial tension, you know their individual components, you know about the Young's equation, so wetting on nano pattern surface, what I talked here, and you also know about the Laplace pressure and the Young-Laplace equation. So, if you look into the content, we are essentially looking back at the content. The next thing we needed to discuss was nano fabrication methodologies, that also we have in fact talked about briefly, about the top down and the bottom up approaches. We already have had an introduction to surfactants and gave you one example of self assembly. So, this is also done. You now know what is CMC, what is micelle formation, what is reverse micelle and stuff like that. So, that also we have discussed. What we are going to, so the next thing that comes up is photolithography, and in the introductory slide itself I had given you an introduction, a sort of a glimpse of why photolithography is important, because though we talked about several application areas of pattern surfaces like structural superhydrophobicity, structural color, nanobiotic application, even metamaterial, I finally told you that the most significant user of nano patterning is actually the microelectronic industry, and the significant progress in nano patterning is attributed. So, we discussed this also very briefly. Significant progress in the microelectronic industry, particularly in the form of faster processors, higher clock speed, is achieved due to tremendous progress in the field of nano patterning. Now, I will not go into the details of the exact physics of what happens, but we understood that, for example, there was an example, some numbers were written. So, a Pentium 2 processor, the line width was 300 nanometer. So, periodicity was of the order of 600 nanometer, and now you understand for an i5 core processor, line width is down to 32 nanometers. So, the periodicity is 64, roughly it is 60. So, in roughly 10 years, where the same area where you could put one PN junction, you are now able to place 10 of those. So, chip size remaining same, you are now able to increase the number of PN junctions, and this is the heart or the basic fundamental that leads to the significant enhancement in the clock speed or the processor speed. So, how it is done? Few interesting facts about photolithography and computers. In fact, the development in the field of microelectronics is significantly attributed to the development in photolithography. The transistor invented in 1947, this is just for your knowledge, this is do not have to remember any of the dates, because we are not learning history. I was particularly bad with all dates and things like that. So, first IC, the integrated circuit, was built in 1960, line width was 5 micron. First IBM PC with 16 kilobyte memory and 4.77 megahertz clock speed was developed in 1981. Line width of 350 nanometer was achieved when the 40 GB DRAM was discovered in 1997. Presently, not presently, in fact, it is 2011 data, line width in i5 core processor is down to 32 nanometer. So, narrower is the size, closer is the packing, and better is the performance, or the faster is the clock speed, or faster is the processor. So, here are again sort of another way of representing the same data. So, 1971 you have Intel 4004, 85 you have the Intel 386, PCs 1997 the Pentium 2, and 2006 this is the iCore 2 processor. So, you see that there are this is the clock speed. So, this is something you all look into, what is the speed of the processor you are going to have. There are two additional information. So, one is the number of transistors, and you see that how exponentially the number of transistors have grown, and there is another information that is given here, and that is the line width. And I am sure now you are already able to follow what is meant by line width, and now you all understand it is this line width, the width of the p type and the n type domains on the semiconductor chip or on the silicon chip, that is actually responsible for all the fantastic performance enhancement that you observe. So, there are lots of these graphs, and Moore's law and stuff like that are available. Moore just is a business or a management guru or something like that. He predicted that the processors number density of processors will double in every 5 years, and microelectronic industry sort of has grown exactly following that roadmap. So, that's what makes Moore's law very, very famous. So, as we had already discussed in the introductory slides, that this is the heart of a microelectronic the processor, this array of p and n type domains, and the technique that makes this or lets us make this is nothing but a patterning technique, and it is photolithography. So, that is what we are going to learn in a very simplistic way, so that irrespective of what background you are from, whether you are a chemical engineer, mechanical engineer, or some other engineering, or you have a science background with some basic high school physics knowledge, you are able to understand what it is. Let me also tell you, photolithography is a very, very complicated process. It is a multi-billion-dollar industry. So, all the chip makers have their own photolithography setup. Things are kept in an extremely secretive manner. Even patents are not filed. So, they are more like trade secrets of a company. So, everything that comes in the open literature is a bit dated. So, nobody actually tells what is the present state of art. And I also have, and it has significant input from various areas like electronics, chemistry, everything is required. But we will take a very simplistic picture and only try to understand the very basic steps that are associated with photolithography, so that if somebody is talking about photolithography, you at least know what are the things that are going on. So, let me get started with this particular schematic, which sort of tells what are the steps you do. But before that, let me just tell you about the philosophy, why you do that. So, you as we already talked about, we would like to have these type of arrays of, let us say, p and n type doped domains, and as I briefly mentioned during the introductory discussion, that they are done on a single piece of silicon. It is not that you bring in strips of p and n type silicon and then try to stitch it. It is going to be even more cumbersome, and there is going to be significant enhanced resistance at the interface. So, that is not the desired thing. So, you would like to have p and alternating domains of p and n type doped areas on the same piece of silicon. So, what you do? You actually start off. So, I hope this is clear. If not, please refer to the text or the discussion we have, the basics of photolithography, or refer to my NPTEL lectures, whatever you want to do. So, idea is that how you achieve it. You start off, and for the example we will be giving, I will show that you start off with a p type doped wafer. I am just showing a section of the wafer. The wafer is typically circular in size, but that does not matter. And what you try to achieve is, you try to do some doping n-type doping in a periodic spatially varying manner by putting the wafer inside a doping or a reactant chamber. Now, issue is if you put the whole wafer into your reactant chamber, you will not get structures like this. What you will get, even if you take a p-type doped wafer, you put it in the reaction chamber and you have strong reactants that sort of do some surface diffusion and you get n-type doping, you are going to have a layer of n-type domains across the entire width. So, the whole purpose is in fact lost. So, how can you do that? You can achieve it in a way that if on your wafer you have some patterns like this, of a material, some material, what material is it, I will tell, that prevents the diffusion of your n-type dopant, and the wafer is open only at these locations. Other areas it is buried under this barrier layer, it is actually called a barrier layer. Now, can you think what you are going to achieve when you put this wafer into this reactant chamber? What you are going to achieve is, instead of a flat wafer, now you have a wafer that contains some barriers, and therefore, if this barrier is adequately thick to prevent the diffusion of this n-type dopants, the doping reaction will take place only at these locations. So, within a p-type matrix you will have localized domains or n-type domains. So, I will just draw an exemplified picture, amplified picture. So, this is how it looks like. So, this is now n-type doped, this was anyway p-type initially. So, in the process what you do is, at each of this interface you create a p-n junction. However, so that is the whole idea. I hope it is clear. So, you have some structures on the wafer, I will repeat it because it is a completely new concept. You take a p-type doped wafer, you put some structures on the wafer and then you put it for this doping. I will not talk about the doping reaction at all in detail because that is not something that is associated or related to this course, but these structures, these patterns allow the doping to take in a periodically varying manner, and therefore, your wafer now has periodic patches of p and n type domains, which leads to the p-n junction. Of course, you need a flat wafer like this for fabrication of microelectronic processor, but you have the barrier layer or the structured barrier layer. So, that is anyway another step where you actually need to remove the barrier after the doping is achieved. So, that is a simple thing. So, if you can remove the barrier, then you are left with something like this. And this cartoon what I have drawn, if you just try to take a 3D view. It should match with what I had shown here. So, now I think you should be able to correlate as to what we are talking. So, this is exactly what we wanted to have, and you see you can do that, but there is some. So, there are processes that are associated. One of the process, of course, is to remove the barrier layer. That is not a very important or not a very difficult thing, but the more critical thing is how to get these patterns. On the barrier layer, and what is the barrier layer for that matter. So, with this much amount of knowledge, let us see how we can start understanding photolithography. So, you start off with a, or I have a sort of a copy of the same thing which I will be using here. You start off with a p-type doped wafer, as I already mentioned. Then you grow an oxide layer on top of it. If you remember that we are talking about silicon, and one of the example in one of the earlier classes while talking about spreading coefficient I gave is that silicon has very high surface energy. So, the moment you take out silicon and expose it to atmospheric oxygen, what happens is you expose silicon to atmosphere, the oxygen present in the atmospheric air immediately attacks this silicon, and on this silicon surface it forms a very thin native oxide layer, and its thickness is of the order of 1.5 to 1.8 nanometer, a native oxide layer. You may already start to correlate that what happens during this stage when you want the doping to take place and you have a native oxide layer. The answer is that, well, the native oxide layer is going to prevent your diffusion, dopant diffusion. So, you need to get rid of it at this stage. But simultaneously, this oxide layer, the oxide is actually used as the barrier, and therefore, you also understand that in order to get to this, you eventually need to pattern the oxide layer. But 1.5 nanometer is too low a thickness to prevent the dopants over these areas. So, what you first grow is on top of this native oxide layer, you first grow some thicker oxide layer. This is a very simple step. You just take your wafer into a oxidizing furnace and you heat it for some time, and this is achieved. So, this is the wafer. First thing you do is you grow an oxide layer. So, that is what is shown in the first and the second stage. But then comes the question, how to pattern this oxide layer? Is there a technique to pattern this oxide layer? And the answer is no, there is no step to pattern the oxide layer. And here you essentially take help of a special type of a polymer which is called photoresist. So, see, I have identified that some of the terms probably you will be hearing for the first time, and one of them is indeed photoresist. So, photoresist, as the name suggests, is a special type of a polymeric composition material that undergoes change in its property upon exposure to light. reality is this is UV light. It is not, though it says I mean the classical definition wise photoresist changes its property upon exposure to light, it is actually UV light, and this is a very practical consideration, because you do not want to work with a material that changes its property when exposed to regular white light, because you will be working in an illuminated room or in the sun or whatever, and if the material composition is such that it changes property to light which has in the wavelength of 400 to 700 nanometer, unfortunately during processing itself your material, the photoresist layer or the resist layer, will start changing its property, and therefore you can't work with it. So what you want is that you want a specific layer which will change its property only when you want it to change, that is, you expose it with some UV light or specific wavelength light, and then only it changes its property, and that is precisely what you do. But the second step is over the oxide layer you actually grow a photoresist layer, you deposit a photoresist layer, and this is not done by any growth process like the oxide layer. This is done by another very simple but very popular and powerful technique which many of you might be hearing for the first time again, is what is known as spin coating. So we will talk about spin coating. Then once you have this photoresist layer, of course what we will eventually discuss that there are two types of photoresist. And what are the two types? In fact, there are several questions in the statement that I have made here. One of the statement is it changes, undergoes change in its property. So what type of change does it undergo upon exposure to light? And this change depends, I mean this change can either lead to strengthening of the photoresist or it can lead to weakening of the photoresist. So there can be two different, completely different types of materials. So it is possible these two possibilities are there. Well, some of you might know or might have already done a search that there are two types of photoresist, and this is called actually the photoresist tone, and they are positive photoresist and negative photoresist. I am not trying to do any mapping of whether a positive, in a positive photoresist it is the ones in which strengthening takes place or it is the one in which weakening takes place, because we will learn it in a slightly different way, and therefore you do not have to really mug it up. But yes, so new thing that we are learning, we are already learning a whole lot of new things in this lecture, is that there is a special class of polymer that is extremely, that is absolutely essential for photolithography, for performing photolithography, which are the photoresist, and this photoresist upon exposure to UV light changes its property, and this change in property can either lead to strengthening of the photoresist or lead to weakening of the photoresist. One can also ask what is strengthening and what is weakening. So typically these are polymeric materials, so I would put strengthening as some sort of joining up or cross linking of bonds. So what will it do? It in fact increases the viscosity. So if you now wash it with a solvent, right, it becomes difficult to dislodge it, because the chains are now bulkier or they are sort of cross linked. And what would be the chemical aspect of this so called statement weakening? Well, it in fact implies that the chains, the polymer chains, becomes even smaller. So it is something like chain scission takes place, and what that means is that once you expose it again to a solvent, and that is a step that is going to be very, very important. We will soon realize it is easier to remove the polymer where the chains have becoming smaller. Chains have become smaller again because of viscosity issues. Viscosity is rather low. So, let us look back into this schematic again. So, we now understand the starting point, we now understand the utility of the growth of this oxide layer, we now understand the utility of this coating of this photoresist. But then comes the question, we have coated a photoresist, fair enough, but what do we do? After all, we wanted to create some patterns like this, but as of now we have not talked about any mechanism how to pattern it. So, in order to, this is something that I will continue in detail in the next class. In order to make these patterns, you need to bring in another piece of hardware element which is known as the mask. So, this mask in fact contains the structure you would like to create. They can have identical structure or some structures which are smaller or bigger, maybe bigger not smaller, and with the help of the mask you actually do the UV exposure to have this periodic variation in property in the photoresist layer first. So, that is what you do up to here. So, in the next class we will understand each one of the process along with its nitty-gritty details and also the remaining part of the fundamental photolithography processes. Thank you.